All right, so now that we've gone through some general concepts, let's look at a solution, or how to solve this problem. And the method we're going to use here is the method of undetermined coefficients. So again, we have our general equation, which may have up to n derivatives with coefficients that are constant. This method works for constant coefficients on each of the derivative terms. And of course, this is the non-homogeneous case where we have forcing functions, and there could be k linearly independent parts to the forcing function. And those k different parts will, of course, give k different non-homogeneous solutions in addition to the homogeneous solution to the general problem. So the problem we're going to look at here is as follows. Let's look at the function y, or the equation, or ordinary differential equation, y triple quadruple prime minus y double prime equals 3x squared minus sine 2x. So we have two forcing functions that you see on the right hand side. And you'll notice that I've jotted down an instruction set that we're going to sort of talk through as we work through this problem. So the first part is to solve the homogeneous problem, find the homogeneous solution. So let's do that here. So we know that YH is proportional to e to the lambda x, and when we plug that into this equation, we get the characteristic equation y to the fourth lambda to the fourth minus lambda squared, and that's all e to the lambda x is equal to 0. And the term in parentheses is our characteristic equation, so we know that in order for this to be 0, the term in parentheses must be 0. So this gives, if we factor out a lambda squared, we get a lambda squared times lambda squared minus 1 is equal to 0. And this tells us that lambda is equal to 0, 0, and then plus and minus 1. And given that this is a fourth order ordinary differential equation, we know we have to have 4 different distinct values of alpha. And the 0, we have 2 zeros, so we have to apply our rule when we have a repeated root. So our homogeneous solution is equal to c e to the 0, right? And this is equal to 1. And I'm going to use, let's use c1 for that. Plus, for our second 0, we need to multiply e to the 0 times x to get the second linearly independent part of the solution. And then we have a c3 e to the positive 1x plus c4 e to the minus 1x. So let's set this aside, and we'll keep that. We know this is going to be part of our solution because our full solution is going to include the homogeneous solution. So we've solved, we found our homogeneous solution. So the next thing we need to do is solve for the non-homogeneous part. So step 2 is to identify the set of linearly independent parts of the forcing functions, of the forcing function. So in this case, 3x squared is definitely linearly independent from sine 2x. So we can easily identify 2 linearly independent functions for the forcing term. And so for that, we know that we're going to have 2 linearly independent non-homogeneous solutions, one for 3x squared and one for sine 2x squared. So let's find the non-homogeneous solution for 3x squared. And so here we are at step 3. Now if you look at this, we have derivatives of y, and those have to sum to give 3x squared. And so it makes sense that the solution, the non-homogeneous solution for 3x squared, are made of derivatives of 3x squared. So the first step to finding the solution is to find all of the possible all of the linear independent functions that make up all derivatives of 3x squared. So for our first function, we have 3x squared. The first derivative is 6x. The second derivative is equal to 6. And then the third derivative will be equal to 0. So step 3a is to find the finite set of linearly independent functions made of all derivatives. So this finite set here is 3x squared. Sorry, let's remove the coefficients. We don't need the coefficients because we're going to actually solve for those. So just looking at the functions themselves, we have a function of x squared, we have a function of x, and we have a constant function which is multiplied by 6. So we'll denote that as a function of 1. And then, so the next thing we do is we hypothesize that the non-homogeneous solution for our first function is a linear combination of those three functions, x squared, x, and then 1. So we've taken all possible derivatives of this forcing function because we know that the solution is made up of derivatives, and so we're going to hypothesize that the solution is indeed a linear combination of the derivatives of this function. And so let's look at this function for a second here. You might recognize that this term bx plus c is essentially the same thing as c2x plus c1, which is in the homogeneous solution. And that seems kind of strange because we know that every part of the homogeneous solution, when we plug it into the left-hand side, it's going to give 0. So we have a good bet that bx plus c, when we plug that into here, is going to give 0. So there's no way that these two can make up 3x. So what we're doing is we're looking for duplicates in this non-homogeneous solution with the homogeneous solution. And we found duplicates, and when we do find duplicates, what we have to do is multiply the non-homogeneous solution by the lowest power of x that removes the duplicates. So if we were to multiply this by x, we would get ax cubed plus bx squared plus cx. And indeed, we've gotten rid of the duplicate with our constant term here, but we still have a cx which duplicates c2x in the homogeneous solution. So the multiplying by x to the first power is insufficient. So we have to multiply by x squared. And that gives our first non-homogeneous solution as ax to the fourth plus bx cubed plus cx squared. Okay, so we now know that we have a solution, and the last thing we have to do is to solve for the undetermined coefficients, the a, b, and c, and we do that by plugging this into our original equation and finding the values that leave us with a 3x squared. So here is our original equation, and when we take our first derivative, our equation was ax to the fourth plus bx cubed plus cx squared. Our first derivative gives a 4ax squared plus a 3 4ax cubed, 3bx squared plus a c 2cx, y double prime gives 12ax squared plus 6bx plus 2c, y triple prime gives 24ax plus 6b, and then y quadruple prime is equal to 24a. And so when we substitute this and this into here and here, we get 24a minus 12ax squared plus 6bx plus 2c, and that all has to equal 3x squared. So now we have to solve for a, b, and c such that this is true. So let's collect like terms of our linearly independent functions, that being x squared, x, and then our constant term. So for x squared, we have a single x squared term, that's 12a, and 12a must equal 3 on the right-hand side to match the x squared term on the right-hand side. In terms of x, we know that 6bx, so we have a 6b, and that's equal to 0. There's no x on the right-hand side. And then we have a constant term, which we'll denote as 1, and that is, what is that? 24a minus 2c. 24a minus 2c, and that's equal to 0 because there's no constant term on the right-hand side. So this equation tells us that a is equal to, this was a minus 12a because we have a minus there. I forgot to write that down. Hopefully you caught that while I was doing it. And so we get an a is equal to minus 3 over 12. And that's, to simplify that, that's minus 1/4. We get b is equal to 0. And we know that 24a, which is 1/4, minus 1/4, minus 2c is equal to 0. And so this tells us that c is equal to minus 24 over 4 divided by 2, and that's equal to 3, minus 3. C is equal to minus 3. And so now we have our solution. We have our first non-homogeneous solution. So it's minus 1/4 x to the 4th, which was a times x to the 4th, and then we might have minus 3x squared. Okay, so now we've solved for our undetermined coefficients for our first non-homogeneous solution for our first forcing function. Now we have to repeat the steps again to find the non-homogeneous solution for our second forcing function. So here we have to find the finite set of linearly independent functions made of all derivatives of this forcing function. So our next forcing function is f2 of x is equal to minus sine 2x. And so the first derivative of f2 is equal to minus 2 times cosine 2x. And the the second derivative is equal to 4 sine 2x. And you can see that if we were to continue to take derivatives, we'd get alternating sines and cosines. So the Li set is equal to, well, we have a cosine 2x and a sine 2x. And so we're going to hypothesize again that our second non-homogeneous function is a linear combination of sine 2x and b cosine 2x. And we have to next we have to do, we've done this, so now we have to look for duplicates with the homogeneous solution. And so we go back to our homogeneous solution, which was this, and we don't see any sine or cosine functions here. So we're in the clear. We don't have any duplications with the homogeneous solution. So we can proceed. So we have two coefficients, a and b, and now we have to solve for these undetermined coefficients, again by plugging this into our equation, and then solving for the coefficients. So we have, so here we have, so y prime is equal to 2a cosine 2x, and then minus 2b sine 2x. Y double prime is equal to minus 4a sine 2x. The derivative of cosine is minus sine, and then we have to multiply by 2 out front here because we have to take the derivative of the 2x here. And then the second derivative of this term is minus 4b cosine 2x. And we would evaluate the third derivative, which I'll let you do on your own. And then finally, we have the fourth derivative, and that's equal to 16d sine, 16a sine 2x plus 16b cosine 2x. So now we have to solve for our undetermined coefficients, a and b, such that when we plug this term into this, and then the second derivative into here, the two will, when we sum them together like this, we get a minus 2 sine. And so this gives us, when we plug those in, we get a 20a sine 2x plus a 20b cosine 2x is equal to minus sine 2x. And so again, we got to collect linear like terms of linearly independent functions. So our first function is sine 2x, and the coefficients on sine 2x are 20a, and that has to equal minus sine 2x. And then our second linearly independent function is cosine 2x, and we have a 20b, and then we have 0 cosine 2x's. So we have 20b is equal to 0. And so this tells us that a is equal to minus 1/20. Sorry, I shouldn't have written a sine 2x here. I should have just written a minus 1, because that's the coefficient on minus 1 is the coefficient here on sine 2x, and so we have to equate coefficients. So this gives us a is equal to minus 20, and this tells us that b is equal to 0. And so our second non-homogeneous solution is equal to a, which is minus 1 over 20 times sine 2x. So now we have our second non-homogeneous solution. And so now we can write our general solution. And our general solution is y, and the first part is our homogeneous solution, and that was c1 plus c2x plus c3 e to the positive x plus c4 e to the minus x. And then we have our second, so this is our homogeneous solution. And then our first non-homogeneous solution was minus 1/4 x cubed minus 3x squared and then our, I could just leave this as a minus 1/4 minus 3x squared, and then our last non-homogeneous solution was 1/20 sine 2x. And so there you have it. This is the method of undetermined coefficients to solve for a higher order ODE with constant coefficients that's non-homogeneous.